Right, so as kind of promised at the start of the term, wanted to talk about concurrency. And so we're going to take a look at the first part of the tour of Go's uh, walk through the features of Go that support concurrency. And then there's some stuff on mutual exclusion that we'll save for a later lecture. I think we have enough from these few slides. So the first thing that we want to cover is the idea of Go routines. This would be something that would be called a coroutine in another language, and so Go for their language. And the way this works is that if you just say Go and then your function call, then you are starting what's called a new thread of execution. In this case, the new thread of execution, if you want to put it in the simplest way possible in terms of what we've talked about so far, is that essentially you need a separate instruction pointer. And so in your program, you're going to have now two copies of the instruction pointer, two places where execution is going on. It's in the same program and it's using the same copy of memory. So it does not create a new copy of all your variables somewhere else. All those variables are going to be shared. And so that's what it means when it says the same address space. Then when we talk about address 1000, then both of these threads of execution are referring to the same, the actual same location. It's not like there's some other copy of all the data where address 1000 is in some different place. So the same values. So on the one hand, that allows us to work together, these threads to work together. And then there is the concern that they may interfere with each other. So as part of the working with each other, then they support different ways that these threads can communicate with each other. So one of the kinds of communication you find that exists is this idea of a stream. And what happens here is that people, or rather threads of execution, programs in other libraries that support streams will write to the stream, and then at the same time, other threads, other programs can read from that stream. And so this is kind of like if you've taken data structures, or actually even in maybe in 201 or something like that, then you would have talked a little bit about the idea of queues, where you have this what's called FIFO, or first in, first out behavior, that when you get in line at a store, then the first person to join the line is the next person to get service, for example. What this allows is that it allows us to kind of separate a bit the part of communication that involves writing and the part that involves reading the message, if you will. So in a traditional function call, then you call the function and then they have to kind of receive the message right away, right? They get the values of the parameters and they do their thing and then they reply back to you, right? And in the meantime, you wait for them to do the function to do their work and come back, because everything is executing with just the one thread of execution. And so the caller is waiting in a way for the function to finish, and then you go back to where you called the function and then you continue, right? That's where you have the return address that gets put on the stack that allows you to continue where you, to pick up where you left off. In this case, then it at least has the potential that we could be writing information onto that stream. And in theory, and with Go, we'll see that there are some restrictions because we're talking about threads. in theory, if you're talking about different programs, then the program that picks up from the stream doesn't even have to be there right now, right? So this is to help to encourage the separation of the execution to represent the idea of how are we doing things concurrently at the same time. So it's kind of like you want to text someone else, and so they don't even have to have, their phone doesn't have to actually be on at the time, right? Maybe they're out of battery, their battery's out of juice or whatever, but it doesn't matter, you know, that's when they get everything charged up and they're connected again, right? You know, even if they're not currently connected to the network, they will get the message eventually, right? So this has a similarity to that kind of communication, as opposed to, you know, function calls being a little bit more like your traditional phone call, where you call and if the person's not there, then, you know, it comes back and says the other person's not picking up, or you just hear the ringing and you stop when you run out of patience, I guess, and figure that the person's not there, right? Okay, so for the streams in Go to work, then you have to create what's called a channel. And this is done using the make command again. And so inside make, you will say make, and then you have to say chan int. So you need the type is going to include chan to indicate it's a channel. And then you need to say what are the type of values that you're going to pass into the channel. So in Go, the streams are what we would call typed. Right? So if you try to write a string to a channel of ints, it will that will fail. And in terms of the syntax for writing to a channel, then you have the channel, some kind of channel variable, and then the less than sign dash, and then some expression. You evaluate the expression, that value gets written to the channel. If you want to read from a channel, then you need to use the less than and dash with the channel on the right side. And then optionally, you have a variable on the left side, right? So sometimes you might want to just write something right away to say, or you might want to pass along that value to another function or something like that. You don't actually have to, you know, write to a variable first. And we'll see examples of the syntax. So there's a small note there on that slide, which is actually important for understanding a little bit better what's going on, where it says by default sends and receives block until the other side is ready. So that the other side has to be a different thread, we'll find. Again, we'll see that in action kind of later. So they have some initial examples to kind of get you warmed up. And so we have this function that is going to add up a bunch of values in a slice, and then write that sum to a channel. So you see here, most of the code at the beginning is similar to how you would ordinarily do this, right? You calculate a sum, initialize the sum to be 0, and then you add up the values from the array. So you're using the range keyword here so that we're going to have the index, which we're not using, and then the value. And so we're just adding up the values. After we're done going through the whole slice, then write that out to the C parameter, which is a channel. So a couple things here. The writing to the channel is an append operation. It adds to what's in the stream. It does not overwrite whatever is already written there. So you don't have to worry about that. And so, you know, in terms of implementing things, it is going to have to potentially save values, and then you're going to be picking up the values when you're ready. The other thing to note here is that the sum function here, its output is going to the channel. It is not returning the value. That's why there's, it's a void function. There's no return type, why there's no return statement in here. So it behaves a little bit more like if we had passed, a variable by reference, and then you're writing to that variable to return something. But the result, the behavior is going to be different. Again, for starters, we're just writing to the channel and adding on to the end of the channel. And then when they make in their main, and I'm removing some of the code to just make it a little bit more legible on the screen, they start off with this this array of 6 values. They and they're making a channel of strings here, and actually that's wrong. This should be a channel of ints. And then we see that they're calling the sum function using the go keyword, and they're going to add up everything up to half of the length of s, right? So len s is 6. So this is the values 0, 1, and 2, everything up to, but not including the element at s3. And then here we have the values starting at 3 and until the end, 3, 4, and 5, and we'll add those up. And then we are going to write those values, or we've written those values inside those functions, and then we're going to read the values out. Right? So we have x comma y colon equals, and then you see here dash less than dash c, less than dash c. So we're just writing the values from the channel into these variables, or reading it into these variables. And then we are taking those partial sums, the sums of each half, and then adding them together. So these function calls can run in parallel, and then each of these calls is working on a separate part of the slice. They're not going to interfere with each other. They're only reading anyway from the values, so that's not a concern. But this is a typical way to break up the work when you're trying to run things in parallel. So there's some of you may have heard of the idea of map reduce as a way to structure parallel computation. And so there is this idea of mapping out the different parts of the problem, breaking it up into smaller parts, sending those parts out to be processed. And then when you get the results for each of the parts, then you combine them together to get your final result. So distributing the parts is the mapping part. And then when you combine everything together, that would be your reduce part. You're reducing a bunch of partial results to a single value. So let's see if we can go to that page. Right. And so you can see here that you've got the sums of the first part in X. Right? Well, actually, I'm sorry. This is one of the halves, and then some of the other half. So you have -9 + 4 + 0. That actually got completed first, and then 7, 2 + 2 + 8. That got completed second, and so therefore the -5 sum got written into X, and then the 17 got written into Y. And then finally you do X + Y = 12, then that's your final result. So this also does point up one of the complications of doing things in parallel is that you can't count on things being done in a specific order. So for starters, even on your machine is undoubtedly a multi-core machine where you have multiple CPUs. So yeah, you could be running multiple threads at the same time with different CPUs executing. And so each CPU can maintain a separate instruction pointer to point to a different instruction in your code. And then of course they are still sharing the same RAM, the same memory. So that fits the execution structure that we're looking at here. So it happened to be that the second half got added up first. In general, it could be first, it could be second. We don't really know, right? And if you've kept up a little bit, if you follow technology a little bit, you know that a lot of software right now is running in the cloud. That's one of the exciting areas for the tech companies to develop things and to get better performance, to run more things in parallel. And so therefore you might have things running on different machines, different really actually physically different machines. And there are, of course, potential to speed things up, and also costs as well, because you have to get information from one machine to another machine. And then you have concerns where you start running stuff on multiple machines, and then suddenly one of the machines crashes for some reason, or you can't reach that machine. Your communication doesn't get acknowledged. And so there are a lot of things that can go on with the hardware that can produce these unpredictable results. So you can get this benefit of faster performance, but you have to balance that against the complexities of running things concurrently. So in our case, again, we're dealing with small lists of values. So it's not something that we're really worried about. Something goes wrong, we reboot our machine and then go again, right? But if you are thinking about things like big data, right, that you could be running programs that take a while, or you might be trying to run something. It's not so much that you need to wait a year for the result, but you are running something where you're going to continue to look for results, and you want things to keep running for a long time. I need to think about your in a way your browser, right? You keep your browser open, you don't shut down the program, typically just leave it running, and so it can be running for a long time. Let's see. Okay, so this is actually I think I got the things opposite, right? So you cannot write a string to this channel. Okay. Okay. So the next kind of subtopic is this idea of buffered channels, and so you can give the channel a buffer so that you can write more values to the channel. However, if you overflow the channel, then your program will block. Right? So the concept of blocking is very important for performance, because we're trying to run things concurrently on multiple machines, multiple processors. If we're blocked, then we're not doing anything on the current processor. So yeah, our code is running on multiple processors, but if there's only one active processor, you're not really running faster. So we start writing, and if you change this code here, this is on the next slide, right? If I write beyond the capacity of the buffer, then it actually is going to block. So if I try to run this here, it says all Go routines are asleep, deadlock. Right? Because if you go back to that comment we looked at earlier, or saw earlier where it said it's going to block, waiting for the other side to be ready. So in this case, we have the ability to write a couple values here, but trying to run more. There's nobody around to read values off of the buffer. And so that buffer is already full. We can't add to the buffer. So we are stuck, and Go fortunately detects that. And so then it will just stop the whole program. So we'll see something a little bit more later on where there's a more practical impact. Where it wouldn't be saw it as here. We're just very bluntly going over the capacity of the channel. So there is a function cap for CH so that you can check the size of the channel. And so notice here it says all Go routines. That's a little bit confusing. Your program is considered a Go routine. Your program is a thread of execution, right? Even though it's only you're only running one thread, but it is still a thread of execution. So you kind of deadlocked yourself. You can close a channel to indicate that there are no more values coming. And that is another form of communication to indicate that. You're not required to close your channel. So it's not like with the files where, if you didn't close the file, then maybe that last line of output didn't make it into the file and things like that. So here, you don't have to actually close it. You can leave it open as long as you need it. But yes, at some point you might know that there's no more data coming. You might, and then close the channel. And this I can test that as well. So again, they use their pattern where they've got two return values when you read from the channel. So the second value coming off of there is that error return value. So if OK is false, then you know that the channel is closed. Similarly, if you use that range keyword, you can use range on a channel. Usually we've seen it on arrays and slices. But if you use it on a channel, then it will keep going until the channel is closed. And so you can print all the values on the channel. And since we are talking about multiple threads of execution, then one of the things you want to try to do is make sure only the sender closes the channel. You can imagine where if you have a reader that's trying to close a channel, there's a couple things that could go wrong. So first of all, maybe the sender still has stuff to send. And so then they try to write to a closed channel, which produces an error. And how do you know that you should close the channel? Maybe you're done looking at the values from the channel, but maybe there are other possible receivers who might want to look at values in the channel. So don't have your receivers close the channel. Even if right now, in the current state of your code, your receiver is done and there are no other receivers, but you don't know if that's always going to be true. The code might get enhanced and upgraded and basically changed over time. And then at some point, someone might want to add in another receiver, and so we don't want to create a problem for that potential scenario. There is a way that a reader can check multiple channels using the select keyword, and this is going to look like the switch keyword, but here you are talking about this concurrent situation where you have multiple channels that you might be checking. And then there is a default case so that if none of the channels have data, then you can go ahead and do something so that you're not blocked waiting. Right? if we look here, then they have this example where they're using the time package to set up timers, to set up alarms, essentially, that after a certain period of time, then something will happen. They'll write to that, that channel. So there's a kind of a different way of using the channels for communication, where you're getting kind of alerts to events. Just run that, so you have that tick, right? So for a while, you're getting this, dot, 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 and then you sleep for a while. So there, again, here we have the kind of 3 threads of execution, because you have the kind of tick thread, the after, the boom thread, and then the main thread. Right? So there's this thing that will go off, and then after every 100 milliseconds, then you get the tick, right? And then after 500 milliseconds, finally, you get the boom. So they'll write to the, after 100 milliseconds, they'll write to the tick channel. After 500 milliseconds, they write to the boom channel, right? And then in the meantime, you're waiting for that to happen. Oops. And then there's, it's covered up here on the screen for me with the Zoom stuff, but you can kind of see there's the boom down there, right? Yeah, there you go. Okay. And so now we're going to spend the rest of the time looking at the binary tree exercise. And so I think this will help us to see a number of aspects of working with concurrent execution. So to start with, I have to recognize that, our course doesn't use data structures as a prerequisite. So you may not have seen trees before. I think it's potentially a topic in 201, but I think most of the time we don't get to it there. So, so we have to look at some of the aspects of what a tree is, and then walk through how we're going to traverse these trees, and how we're going to compare the 2 trees to see if they have the same values. So first of all, what is a tree? So a tree is going to be something like, for example, your file system. You might have a family tree that you had to create in, I don't know, grade school or for personal interests. We have the basketball championships that are going on that are take place over multiple rounds, and they're knockout in the sense that whoever loses is out of the tournament, right? And chess tournament, not so much chess tournaments, tennis tournaments tend to work like that as well, right? Where you have a bunch of players, and then you pair them up, and whoever wins gets to the next round, and so on and so forth. So each item in the tree is called a node. So in your file system, each of the nodes would be either a directory or a file. In a family tree, then each node would be like a person. And then you have in the championships, those competitions, then each of the nodes would be either a team, or most of the nodes are actually the games, the matches where they have to compete against each other. There is a root in each tree. That's kind of the starting point if you're talking about like a file system or a family tree. For a file system, you have your root folder, right? So, depending on whether you're on a Linux, Unix system or on Windows, it's backslash or slash, right? And then you have the end point if it's talking about like the competition, right? So that at the end of the competition, there's going to be one champion for, one champion college men's team, one champion college women's team. Now, for their examples, they're talking about binary search trees. So let's take a look at their examples, right? So in this case, each of the nodes represents a number, and it's binary in the sense that each node has two kind of children. So again, if you kind of map this to how like your file system might look, it can be similar where we have a root folder and then there are subfolders or subdirectories at the root, and then they have subdirectories and so on. And then you have those nodes at the bottom that are called leaves where they have no children. So for a file system, the leaves would be files, right? Because files don't contain other files, right? Folders or directories contain other folders or files. For a family tree, you kind of have to flip this upside down where there's you, and then there are your parents and their parents and so on. Right? And then for the, like the college championships, then you have your early round games, and then the round of 32, then the round of 16, round of 8, round of 4, then you have the semifinals, and then you have your final championship. It is, besides being a binary tree with two children for each, up to two children for each node, then you have the fact that it is what is called a search tree. And a search tree means that it is an ordered tree. So we notice that everything that is to the left of 3 here, that's what we might call the left subtree. If you see the left side here, that's structured like a smaller tree. But everything here is less than or equal to 3. And we see that even with ties, right? Everything down here is less than or equal to 1. Everything here is greater than 1. And similarly over here, everything here is greater than 3. And then we have the same values, but in a different structure, right? Where the 8 is at the root, and everything to the left is less than 8. Everything to the right is greater than 8. Okay. Now, if we want to compare two trees for the same values, it helps to talk about what it means to traverse a tree. So to traverse a tree is to visit each of the nodes. There are different algorithms, different orders for making sure that you get to each and every one of the nodes, both the nodes that have children and the leaves that don't have any children. The nodes that do have children are called inner nodes, incidentally. So the traversal that we're interested in here is what's called in-order traversal. So going back to this picture here, if we visit things in order, what we do is we visit the left subtree first, then we quote unquote visit the root. We can output or examine or process the 3, and then we process everything in the right subtree. So if we do that, then that means that the first value that would get displayed or processed is actually this leftmost node, which happens to be a 1. If we do the same thing with this right tree, the tree on the right, even though everything is structured differently, right? We have to do the left subtree first, we have to do the left subtree first, left subtree first. So we still do that leftmost value, the 1. Right? And then you go back and you do its parent and you output that. And then you go to the right to see what's in the right subtree. And then we go back here and then we go through the right subtree again in the same order. Here, we go to the right subtree, then we go back up to the parent and then to the right subtree, parent, and then the right subtree. So we're always visiting the left subtree first. We finish everything in the left subtree, then we see the value, and then everything in the right subtree. So if we do that, then regardless of how we order these values, because it's a search tree, so it's ordered, then if the two trees have the same values, we will output the values in the same order. So we'll end up with 1, 1, 2, 3, 5, 8, 13, just like it says here, right? It is storing that sequence. And this one will be 1, 1, 2, 3, 5, 8, 13. Okay. So when they have you do this as an exercise, one of the first things that's nice about this is that they don't try to write the whole thing all at once. And they make sure to test things along the way so that they don't let you go ahead and eventually write everything before you've seen whether things are working. So you want to write the walk function first, then test the walk function, right? So that's actually, a good lesson for real life, that when you go out and you do code, you want to test things as you go along to make sure you're on the right track. You don't want to work for 2 weeks and then figure out that you did things the wrong way, and now you have to go back and try to fix things, right? Because other people may be waiting on you, your company is waiting on you. You may not get too many second chances to show that, yeah, you actually do know what you're doing. So test as you go along. That's a good lesson, even for your work in school, even though the exercises are shorter. Even if your time doesn't allow you to do things until you only have the one time slot for it. During that time, it's good to try things out as you go along to see, are you on the right track? So first we have our walk function, and we want to do things in that in order way. So the actual very first thing we need to do is to make sure that the tree has values in it, right? Because if there are no values, then we shouldn't be trying to do anything. So we do check to see if the parameter t, which is the root of the tree of the subtree that we're working with, could be the whole tree, could be some part of the tree, could be, again, when we get to the leaves, when we're ending up trying to look at an empty tree. So we check, is it an empty tree? Is it equal to nil? If it is, just return. Okay, again, we're working with channels. Our output, the way we'll quote unquote return values is through the channel parameter. After we've confirmed that this tree is not empty, then we visit the left subtree by doing a recursive call to walk. Right? So, and we want to do it on t.left. We don't want to do it on t because then we would recurse infinitely. We wouldn't stop. Right? So we want to look at the left subtree first, pass along the same channel because we're writing to the same channel. Then, write the value at this node to the channel, and then visit the right subtree by calling walk on the right subtree. And then it says test the walk function. So they have their implementation of the tree struct has this new function that allows you to get values from 10 values in some random structure for the tree. And so you get the values, k, and then 2 times k, 3 times k, and so on. So if we do this here, then we should see that we have the values 1 through 10, okay? Because we're saying tree.new 1. We pass that into the walk function with the channel that we create, and then afterwards we're going to read all the values out and display them. Okay, and yay, it is in fact what we see. So notice that the values do in fact come out in order, again, because of the way we structured walk. All right, let me make sure there weren't any points that I wanted to make that I forgot. So we do have to import the format if you're doing it from the displayed stuff that they start with. Then you do need to import the format package, and you're commenting out the same function because you're not actually doing anything with that right now. And so they tell you to call walk using the go, right? So one thing that might be worth noting is what if I just call the function here, right? Well, I get that all go routines are asleep message again. And that's because remember that when you write to the channel by default, you block until the other side is ready. And again, if I don't have that go there, then I only have one thread of execution running, one go routine running, the current main thread. And so Go is going to detect that you wrote to the channel and nobody is waiting to read from the channel. So it will stop the program because you can't go forward. Right? Once we put the go in there, what we're doing is we're taking that tree walk and putting that into a separate thread. So we're creating that separate instruction pointer to walk through the thread. And meanwhile, the main thread becomes the other thread, the receiver, so that when the instruction here is executed to write, in our case, the 1 to the channel, there is a receiver that will be ready to actually do something with it, which is the main thread. And it will go ahead and write out that first value, and then the walk can continue to write the second, write the 2, the 2 to the channel, and so on. Right, so that go there is absolutely critical for making this work. Oh, right, there is an alternative that you could do to get this to work out is if you don't put the go here, but you make the channel a buffer channel and you make it 10 or bigger. In this case, the channel is buffered now. And that means that when it's writing values, the channel is able to accept it and accept more values until, again, that buffer is full. So you can write up to 10 values here without blocking. And that will allow this single thread to go ahead, write the 10 values to the channel, and then come back and then read the same values from the channel. It's not very fast, but then it would actually work. Right? Let me get the 10 coming out. Okay. Step 3 is now to implement the same function using walk to determine whether T1 and T2 store the same values. So we have a few ways of doing this because we have now the 2 channels that we're going to compare. And so one thing that we could do is saying, okay, I have these channels. Let me read those values into slices, right? Save those values up into the slices. And then now I have 2 slices. Now I know how to compare those, right? I know how to deal with that because that doesn't involve any kind of parallel processing or anything like that. So, it's good that that's something that can make sense to us. The catch is that we do need to wait for all of the values to be generated before we do any comparisons, right? So let me go ahead and show you that approach. There's tree 2. Copy that to here. Okay, so we go through and we have our 2 arrays, and we have to know that both of these are exactly 10 elements long. And so I read the 10 values from channel 1 into the vals, vals 1 array. And then I take the stuff off of channel 2, write that into the vals 2 array, and then I loop through those values, comparing them. And if I see anything that's different, then I come back with false. Otherwise, if I make it through all of the values without seeing any differences, then I can return true. And so now we're going to test this, and the way they want you to test this is by using same with tree.new1, tree.new1. So you'll have the same values there, just in different structures. And then same tree.new1, same tree.new2 will have generally different values, non-overlapping values. So there should be some differences there. So we're going to print out what's the result of calling same with tree.new1, tree.new1, and then the same thing, tree.new1, tree.new2. So that's, by the way, again, a good example when we're testing any function that has, kind of true and false as a possible result, or some other kind of yes, no, or anything like this where it's a, either or kind of thing. You want to test both the either and the or, right? You want to test both the true and the false cases to make sure that both of those scenarios are done correctly. Right, so we see, in fact, that new1 is equal to new1 and new2 are not the same. Okay, so so that works. We got the right answer. One of the things that we want to do is to start thinking about, for concurrent execution, the reason why some of those programmers get so much more, so much higher salaries at some companies is because they can handle more complex things, and not just getting something right, but doing things well. One of the things that overall you kind of see in technologies where earlier people would tend to go with whatever approach would be safer, would be easier to get right, because people kept getting things wrong. And now they have experience with things, and they're like, okay, we could try something harder. And so that's why you see that people are willing to try these more complicated approaches with concurrency, when it makes sense, by the way, right? So again, it's important to stress that if you can get perfectly good performance with a simple code that doesn't use, quote unquote, advanced features, then do it, right? Don't try to do stuff that you don't really need. Your companies are not interested in doing things so that you can learn new things. They want something that works. Okay. So so to try to do this better, then we should not be satisfied with the fact that we just got the right answer, but we should think about, well, why not start comparing values once I have something in channel 1 and something in channel 2, right? And so then I can replace, and of course, there's also a lot less code here. I don't have to write all that stuff to read it into the 2 arrays and things like that. So I have less code to write, which I think I did not note later, but that itself is a benefit. The more code you have, the more likely it is that you have bugs in the code. So it saves you time typing, it saves time testing, because there are going to be, in general, fewer bugs to deal with. And they'll run faster. So all these benefits. So I had everything set up in this tree3 file. So I'm gonna just do that and show you that, yes, that actually still runs correctly. Right, so we have this much shorter same function. And I get the same results. incidentally, this is something that has applied not even when we were dealing with all this, parallel execution, coroutines kind of stuff. But this has actually been true for a while in, say, databases. So if you go through the documentation for the Oracle database, which historically has been the really successful relational database, they have two different modes of execution. That when you're writing code to query their database to get results, extract information from the database, you could either try to do things to spend as little time as possible to, as quickly as possible, get the entire result and then produce the answers to you. Or you could try to speed up the extraction of the first parts of the result as quickly as possible. So the results from a database query are in the form of what are called records, which for our purposes are just kind of like rows of information. And so you can think of, like, say, the products that you get from, well, like a product search on a site like Amazon. And so you could try to get just some results quickly, that first page of results, perhaps, right? And that brings up why that kind of execution can be appealing, because it doesn't matter, the second, third, and fourth pages. It doesn't matter if you can get all of those pages of results faster. What people usually care about is whether you can get that first screen, that first page of results up quickly enough. And so that's something that is kind of tied into what we're doing in this example, where we're trying to quickly get some results up. And in our case, it's actually going to speed up the overall performance as well, because now this is going to free up those threads faster, that will grab those first values off once they're available, and then they can go and generate the next values. There is still a little bit of blocking potentially if, for example, the first call, the walk T1, CH1, for example, if it's written the first value already, it's ready to write that second value, but the other call to walk hasn't gotten a value up yet. And so in that case, you have potentially multiple values that could go into the first channel, but the other information is not ready yet, and so the main thread cannot actually read values off to do the comparison. And that's where potentially buffering the channels could help with performance. Here's a catch, of course, that buffering means you have to save some values. You have to have some additional memory space to save those buffers. So there's a balancing, right? That balancing act where if it's a small buffer, then it's not going to be, shouldn't be a big deal, right? That we can pay that cost to get the better performance. Too big a buffer though, and then you have a potential of creating some memory issues where you're using up too much of the memory. If we're dealing with 10 values, right, almost none of the stuff that we've talked about really matters. Right? You can see even when we tried to make things as slow as possible, it came back pretty fast. So, so the thing is that, of course, if you're dealing with a lot of data, then you're likely to notice a bigger issue. Now, in this particular case of comparing trees, I'm not sure if comparing trees of 1 million elements each is something you're likely to be doing. But there are going to be cases where you do have millions of elements, billions of elements potentially. And so then, trying to manage that, right? Trying to avoid using too much memory for that, and yet, maybe allocating some buffer space to speed things up would be something that that would be valuable, would be worth the trouble. Okay, so I think there's enough here to go through and think about. So we'll stop for this lecture.